So what we've done in the course, just to review, we focused on the simplest quantum systems at the beginning, the one-dimensional particle in a box. We talked about particle in a ring. The math related to that is in the few chapters of my book that I put up on Blackboard. Then we applied symmetry to that to understand the role of symmetry and simplifying our calculations. And we saw that it took 6 pages of calculus and reduced it to a very small post-it note for the one-dimensional systems. Then we applied it to vibrations. And so this last test, as you know, was on vibrational spectroscopy and row vibrational spectroscopy, where we combine vibration and rotation. So we're kind of moving up the energy scale. Part of that was talking about rotation. So rotation was let me back up. Translation is the smallest energy difference, and we have a hard time. In fact, I'm trying to think of any experiment that we've ever measured that was able to measure the energy difference in translation. It's so small, we have a hard time devising an experiment that can measure energy differences that small. So we really just treat that as a continuum of possible states. We believe that they are quantized for various reasons based upon heat capacity and the behavior of bulk systems at really cold temperatures, but it's not really a spectroscopic measurement that we've been able to pull off to measure the energy differences in translation. But for rotation, very easy to measure those rotational energy differences. Those are in the microwave region, a low energy frequency spectrum. And then we go into vibrations, which is in the mid-infrared. And now we're in the electronic spectroscopy. So we'll start with the data. We'll look at electronic spectroscopy of atoms and molecules. And then we'll finish up the course with the theories of bonding. So how do these electrons keep the molecules together? So we've sort of worked our way through data, rotational data, vibrational data, electronic data, and then we're going to end up with molecular orbital theory and understanding how the electron orbitals that we determine from spectroscopy, how those orbitals combine to hold molecules together. So we're getting close to understanding how molecules are held together. So let's go back to the beginning and look at the hydrogen atom. So the hydrogen atom, thank you. Hydrogen atom, being the simplest atom, is still a very complicated system. One of the things that makes it complicated is that the potential energy is not zero. Can I get somebody to go back and close that door, please? Thanks. So that was the thing that made the particle in a box so easy, was that the V part of the Hamiltonian, the potential energy, was zero. So we could just ignore it. But in this case, we have a proton and an electron, and we have the Coulombic Contraction. And so this is the equation from physics for two charges, opposite charges attracted to each other. You have here the elementary charge. And so that would be the negative charge on the electron, positive charge on the proton, but they have the same numerical value in coulombs, just that the electron is a negative value. If we have, let's say, 3 protons in the nucleus, it's going to be 3 times that elemental charge. And so this Z right here is the number of protons in the nucleus. And so that takes into account, the size of the atom, or size meaning the number of charges, and also the identity of the element. But we're dealing with a hydrogenic system. So let's take helium, for example. It's got 2 electrons in neutral helium, but if we strip 1 electron off, it's a hydrogenic system. It's a nucleus and an electron. Now, the nucleus can be multiple charges, but it's still what we would call a hydrogenic system because it only has 1 electron. And so here's the Hamiltonian. We have the kinetic energy part, this T piece, and then the V piece, which is the potential energy. The potential energy piece is this Coulombic attraction. The kinetic energy piece is this h bar squared over 2m, very similar to the Hamiltonian in our particle in a 1D box. And this del, upside down delta, just takes into account that you are taking the second derivative over all space. So it's not just the second derivative with respect to x like we did in our single dimensional system, but it's, in this case, spherical harmonics, it's r, theta, and phi. Now for the reduced mass, for a nucleus, it's pretty simple. We have the mass of the proton, the mass of the electron. The proton is 1,000 times heavier than the electron, and so it's essentially the mass of the electron. That's close enough for us. And so this is the Schrodinger equation. Notice it's got a little bit of extra piece. It's got this potential energy piece. Now the early mathematicians, in looking at this vector eigenvalue problem, recognized that the spherical harmonics here, this group right here, the spherical harmonics would be solutions to this wave equation. And the chapter, even in the graduate book for molecular quantum mechanics by Atkins, has a little paragraph that says they recognized that these functions would be a solution to this problem, rather than just kind of hacking their way through trying to find a suitable wave function. They just grabbed these spherical harmonic wave functions, and they knew that it would satisfy these conditions. And he writes this funny little paragraph. It says, "Solution by recognition is not to be mocked," or something like that. Like, this is how professional mathematicians do it. So even in the graduate book, Atkins, there was really no derivation as to where these spherical harmonics came from. It was just that they recognized they had the properties that a spherical system would have, and that they would be solutions to this kind of problem. Now let's think, though, we kind of skip over this in chemistry a lot, and we've introduced these wave functions to you at the freshman level. Even in Gen Chem 1, you saw the shapes of the orbitals. But today I'm going to try to open your eyes as to what this means, and it's buried in the name the spherical harmonics, this piece right here, this YLM value. And so this Y function is called the spherical harmonics, and that's the angular dependence upon that orbital, so the theta and phi dependence. The R is the radial distribution, and that's just a function of distance from the nucleus. So that's kind of nice. That's a one-dimensional problem. But then the spherical harmonics take into account the longitude and latitude of this orbital. So think about the electron cloud around the nucleus. It's got longitude and latitude, that's theta and phi. And then it's got, like on an Earth system, it's got altitude, right? That's R, that's distance from the center. And so we separate those variables too in our thinking. If I want to know my coordinates, I got to know my altitude above sea level, that's my R value. And then my longitude and latitude are going to be my theta and phi. So they're treating the electron cloud just like we treat our geography. And so we end up with these quantum numbers. I think on your version you don't have the little quantum number listed by N or by R. So go ahead and put N on your little R there. And then we have L and M sub L up here. So those are our three quantum numbers that we have for our orbitals. Okay, so let's look at this energy equation that comes out of the Schrodinger equation. We have the principal quantum number in the energy equation right there. So that's, and even though L is present in the potential energy portion of the Hamiltonian, it's not in this energy equation. It does not for one electron atoms, but when we get to two electron atoms, then we'll see L and M sub L. Okay, so let's compare this energy to our particle in a box energies. So remember from the particle in a 1D box, and if you want to write that equation over on the side for comparison's sake, it seems backwards, right? To this new energy equation seems backwards because look, the n squared's in the denominator, whereas in the particle in a 1D box, it's in the numerator. And the mass up here, mu, is in the numerator, whereas in the 1D box, it was in the denominator. And there's really no L in our elemental system, But, you know, as you add charges to the nucleus and so on, you're going to be adding more electrons and so on. I mean, that is somewhat of a size thing. And so the charge of the nucleus is charge squared. That's kind of interesting because here we have L squared. So we have all the same kinds of pieces that we do in our particle in a 1D box, but they seem to be upside down. But look here, there's a negative sign here. Okay, so that fixes everything in terms of this inversion. So if we look at this and we say as mass goes up, the energy should go down, right? Mass is in the denominator for our particle in a box. As mass goes up, energy goes down. But same here, as mass goes up, the energy becomes more negative, and so it's going down. As quantum number goes up, energy should go up. Just like in our particle in a 1D box, it's in the numerator. We increase the quantum state, energy goes up. Well, over here, it's in the denominator. As we increase the quantum number, what happens to that ratio? It gets smaller, and it gets less negative. Okay, so energy goes up as we increase quantum number. And nuclear charge, as it goes up, energy goes down. So, you know, we increase the charge, we get lower and lower energies because we have an electron attracted to a more positive thing. And so it's going to be a lower energy. So all of the kinds of mental intuitions that we have from the particle in a 1D box still match what we see in a really complicated system, a three-dimensional atomic system. So you can just rely on that. If the mass goes up in your system, you've got a molecule and now you've got a bigger molecule, your energies are going to go down. Okay, and your energy differences are going to go down. And remember, say it with me, a transition is a difference in energy states. So if your masses go up, your energies go down, your differences go down, and all of your peaks are redshifted, right? Because they go to longer wavelengths because the energy differences get smaller. And if it's a smaller energy difference, it's a redshifted wavelength, okay, for the transition. Okay, so let's look at this radial wave function plotted. We have the this is the probability distribution, so it's the wave function times itself, and it's showing this plot if we just look at those exponential wave functions. But if we take into account the volume element, so, you know, as you get further and further, if you take a dr and d theta and d phi, it's kind of like a three-dimensional pi wedge, right? As you get further out, those angles incorporate a larger volume, right? So if you got a 1 degree difference by your, you know, you're instead of dx, you have d theta and d phi, and it's 1, say. As you get further out, a change in 1 degree from the nucleus is huge. But as you go to 0, what is it? It goes to 0. And so if you take into account this probability distribution with the element of volume, then it goes down to 0 at the nucleus. The reason you need to take into the account the volume element, remember this is the wave function for the electron. If I square that wave function, I have the most probable position of that electron. And what is this telling us? Where is the most probable position of the electron? What is radius? That's distance from the nucleus. So what's the most probable location of the electron? In the nucleus, right? But as we integrate that, as we look at that, if we take into account the volume element, the volume that electron can occupy goes to 0 at the nucleus. And so it seems like a little algebraic trick to just say, yeah, it would go to the nucleus, but there's no room there. All right. So there's some maximum value before it turns around and goes back to 0. And so this would actually be the most probable location of the electron. And for a hydrogen atom, it's this hydrogen radius. That would be what we call the radius of the hydrogen. You know, it's alpha, or A naught. It's a half an angstrom. So that's the most probable distance of the electron from the proton in a hydrogen atom is half an angstrom away. You put these together, they kind of touch, and you have a 1 angstrom bond distance for a hydrogen molecule. When they start to share the electrons, it shrinks a little bit. I think it shrinks down to like 0.7 angstroms. So that's the most probable. Notice that there's quite a range of, that electron cloud is pretty soft and puffy. It's not like a real sharp rise and a real sharp, the radial distribution doesn't look like this, is what I'm trying to say. Right? That's where the electron is. No, it could be pretty far away. It could be, it could be 2 or 3 angstroms away from the nucleus, or it could be really close to the nucleus, but its most probable location is the maximum of this curve, which would be half an angstrom away. Now, as we get to larger and larger atoms, this radial wave function, as you might imagine, as we increase the quantum number, we start to get nodes, right? Just like we did for our particle in a 1D box. As we went up in quantum excitation, we got more and more nodes. Now, these nodes look funny because it's the outer end of that wave function is loose. It goes to 0 at infinity, but it's sort of like it's not pinned to 0. It just eventually has to go to 0 at infinity. So it's pretty loose. As the electron gets farther away from the nucleus, it has a lot of freedom. And so that's why these wave functions tail out so badly. They're pinned to 0 at the nucleus, but out here they're kind of free to oscillate, and so it seems like they're stretched out pretty far. Remember early on I said, what's the most probable location of the electron if that red ball at target was the proton? So if we're here in Huntsville and we go to the target, we see that big 1 meter ball in front of target. If that's the proton, where did I say the most probable location for the electron was? It's like a 71-mile diameter. And so that goes from Madisonville down to Spring, if you're familiar with I-45. And if you're going east and west, it's Navasota all the way over to Livingston. Yeah. So it's a pretty big area. And that's just one electron. What if we go to, what was it, sodium? Yeah, down on the third period. So that would be the 3s electron. Here's the most probable location for the 3s electron. Look how many multiples of that it is. How much bigger it is than the hydrogen atom. That's a long way away. And it's like down in Argentina. Okay, so that 1s electron for the sodium atom is way far away. You ever wonder why it's so easy to ionize sodium? So the hydrogen's like to that 3s electron, you don't come around much anymore, and eventually he just never comes back. He's so far away. So that's the way it is. You can see the nodes. So as I go up to the 2s, there's one node here. And then as I go up to the 3s, there's 2 nodes. There's a node there and a node there. It's kind of strange. Even though that 3s electron stays away from the nucleus very far, there's also a small probability that it's going to be closer to the nucleus in some time, closer than the 1s. So it's a real dysfunctional relationship with that electron. It's really close sometimes, and then way far away a lot of time. Okay. Then let's look at the 2p. So we go up and different L quantum number, and the first available p orbital, which we'll figure out why that is in a minute, has no nodes, no radial nodes. Okay, but look at the 3p. The second available p orbital has 1 node. So you can't just look at the principal quantum number 1, 2, 3, or whatever and tell how many radial nodes there are. You've also got to know if it's a p orbital or an s orbital. But here's the principle that you can remember. The first available orbital of that type, so the first s orbital, the first p orbital, the first d orbital, those have 0 radial nodes. Okay. So I'll circle those, the 1s, the 2p, and the 3d. Does that make sense? Do you ever understand all the pieces? The first available orbital of a given type has 0 radial nodes. You don't see the radial nodes in our drawings, and so this is just something you have to know, okay? Because we draw the little dumbbell shapes and so on for orbitals, but when you draw that shape, you can't see the insides of them, and the insides are where the radial nodes are. Okay, so let's look at a radial node of an s orbital. Okay, so over here on the left, it's showing, without the volume element, it's showing the 1s orbital radial distribution function. And then over here, it's showing the 2s orbital. So it should have a node. So right here in the middle, we have this radial node. What do you think the 3s orbital would look like? It would look like something like this. It would go down below, and then back above, and then down to 0. Okay, so it would have 2 nodes. And so if we were to draw that from the middle, it'd be here, and it'd be here like that. Okay, so these are the fuzzy regions. Kind of making it look like this picture on the right. Okay. That's not a very good drawing, but that's what I've got. Okay. Okay, so let's talk about these other types of orbitals and where they come from. The principal quantum number is in the radial distribution function, or the radial wave function, which is what we've been talking about. So that's just the distance from the nucleus. We call that shell. So these are the shell numbers. So shell 1, 2, 3, 4, 5. And then we have the angular momentum quantum number, which is L, and that describes the shape of the orbital. And scientists, they try to systemize things. They don't want to be confusing, and so you may think they are very confusing, but they try to simplify things. And so if we've got all these numbers, they started saying, well, let's make a combination. Let's use numbers for this and letters for that. And so in this case, they didn't want to confuse L with N, and so they put letters associated with L. So you've seen SPDF and all of that, but that S goes with L equals 0, P goes with L equals 1, D goes with L equals 2, F, L equals 3. And I always count these on my fist. This is very simple stuff. This is like freshman chemistry things that I tell the freshmen, but I like my PChem students like it too. So this is S. It looks like a sphere, right? P, D, F. So I know that F has a quantum number 3, but you have to start with 0. So S is 0, P is 1, D is 2, F is 3. And I always love it to see on the exam, people are looking at it like, okay, and writing it down. And they're doing the spinning things with the molecules. So it's fun to watch you take tests because you'll learn. And then you have all these little nervous quirks that you do. Okay. And so then, but this is an interesting set of numbers because notice that it doesn't go to infinity, right? Here, these 3 dots means it goes to infinity, theoretically, right? You could have an electron that's at an infinite quantum state. But this one doesn't go to infinity, it goes to n minus 1. So whatever n is caps L. So that's why we don't have a p orbital in the n equals 1 shell. Because if it's n equals 1, then L is capped at n minus 1, which would be 0. So we only have an s orbital for n equals 1. And then for n equals 2, what's 2 minus 1? 1. And so we could have a p orbital on the n equals 2 shell, but we can't have a d. Okay, so that's why we have this restrictions on s, p, d, f, and so on. It's based upon this restriction of angular momentum. And then we have the magnetic quantum number, and there's the clue in that name. We don't see an energy difference on these quantum numbers unless it's in a magnetic field. Okay, so that's where so these orbitals have the same energy if they're not in a magnetic field. And this describes the relative position of each orbital. And this one is capped as well. Notice there's no numbers given here. It's a range based upon L. So minus L plus 1, all the way out to L. So notice we have to sort of have we have the max and the min, so minus L to plus L, and then integer differences between. We just increment by 1. And then we have the electron spin quantum number. So electrons come in 2 flavors, spin up or spin down. And they called it spin because it has an intrinsic angular momentum. So that's the actual name of it, intrinsic angular momentum. But where do you get angular momentum? You get angular momentum from spinning things, right? And so they called it spin. But that's confusing because it's not like you can see this electron ball spinning, okay? But you can see the effect of its angular momentum. And so it has intrinsic angular momentum, which means built into the particle is this angular momentum piece, and there's plus or minus a half a unit of angular momentum. So those are all of our quantum numbers, and this is how we systematically write them, right? We have the principal quantum number n, we have the lowercase spd or f as the angular momentum. We could put the specific orbital, the m sub l, down here as a subscript, and then we could put the number of electrons in this type of orbital up here. And there, the Pauli exclusion principle up here is a governing factor that no 2 electrons can have the same 4 quantum numbers in a particular system. So that means there's a maximum of 2 electrons in each orbital. If we were to put a third electron in an orbital, it would have to be either spin up or spin down, and it would have all 3 of the other quantum numbers the same, so they can't have 4 of the same quantum numbers, and so we can't put that third electron in any orbital. So that's where these designations come from. Hopefully this was review, but in a little more detail than you typically get in the freshman course. But is there anything I can clarify right now? Because we've got all of the quantum numbers, and we'll start looking at the shapes of the orbitals next. But you need to know this page like the back of your hand. This has to be part of you. And know how to work with it. So if L equals 3, then you need to know how to do this, right? What's the minimum or the most negative m sub L could be? Negative 3, okay? And then what's the maximum it could be? Positive 3. And so then what are all the numbers in between? Notice how I'm doing this. Do the limits first, and then fill in the middle. So then it goes minus 2, minus 1, 0, 1, 2. You can put your commas in there. Okay. So how many of these, what's the degeneracy of this? Like how many of these orbitals are there? It's 2L plus 1, right? So it should be 7 of these, and there are. There's 1, 2, 3, 4, 5, 6, 7. And those are the F orbitals. That's why we have 7 F orbitals. Each one of them has a different m sub L. So that stuff you've got to be able to just know, okay? And you need to know, why do we not have an F orbital, like a 2F orbital? Well, because L is limited by that number 2. So the maximum we could have is an L of 1. Okay, so the max we could have in the 2 shell is a p orbital. Okay. If you want to close that one too, you can. It's just to you. Okay, so let's look at these orbitals. Here's some p orbitals. Now, Remember the name of these things. What is this part of the wave function called? Let's see if you were listening a few minutes ago. So the wave function is broken into two pieces. We talked about the first piece, which was the radial distribution function, or the radial wave function. What was that second one called? No, there was two pieces multiplied by each other. It said wave function, or psi, equals r and y. What was the y piece? It was YML. The spherical harmonics. Put that word in your head. What is a spherical piece? What's a sphere? Think of a sphere. What does the harmonic piece mean? Chew on that word. What does harmonic mean? We've heard that word before with vibrations, didn't we? And what was it? It was an oscillation. So harmonic oscillation. What do you think spherical harmonics means?
Oscillation of a sphere?
Yeah, and specifically a spherical shell, something really thin. If you think about a spherical shell, so you have a really thin spherical shell. Okay, have you ever blown bubbles? Okay, you blow a bubble, now you've got this bubble in space. It oscillates, doesn't it? In fact, there's lots of ways it could oscillate. And that function, the spherical harmonics, tell you all the ways that that bubble can oscillate. And what we see here are plots of that sphere oscillation. So let's look at this one because I think it's probably the easiest to draw. Draw a sphere around this guy. Okay. And then I'm going to draw a little ring around the equator here. Now, if I blew a bubble, and right as I blew a bubble, it snapped where it was vibrating up and down in the z-axis. I'm going to draw that vibration in a different color. So I'm going to I'll just pick green here. So if I take a snapshot and it's deformed, it might be bulging out on the top like this, kind of like an egg, and be kind of smaller on this end. Okay? Let's say I had a really fast camera and I took a couple of pictures, a couple of frames, and at some time later it was bulging out on the bottom, okay, and not bulging at the top. So I've drawn two frames on there. You see that thing is expanding on the bottom and shrinking on the top, and then sometime later it's expanding on the top and shrinking on the bottom. What's it doing around the equator? It's not going away from it's not going away from the center at all, is it? Okay, so that's a node. That's a part where it's not moving. Remember a wave function, if it's oscillating like this, if there's a place where it's not moving, that's a node. And so in a spherical wave function, if there's a place where that's not moving, that's a node. So how do we get this shape right here? So I'm going to take that sphere. Okay, I'm just going to draw this right here, and I'm going to draw the next one. Let me see. How do I want to do this? Let me change back to red. Okay. So here's the node. Okay. And then here's the perfect sphere. The green is the deformed one. Okay. And here's the center. And I'm going to plot around this whole thing. I'm going to plot these little arrows, the magnitude of these little arrows. So the deflection of the sphere. And then over here, these arrows are coming towards the center, or the nucleus. And so down here, these changes are negative. Can you see that? Right? If I'm plotting the distance from the nucleus relative to the original, so the sphere that's not moving, I'm comparing the motion of this harmonic to the neutral position. And at this time, it's negative. It's closer to the nucleus than its neutral position. It's a smaller radius in that direction. What about the others? It's positive. So these are positive deflections. Think of that word deflection. This is a positive deflection. Okay. And if I plot those deflections, this is what I get. I get this thing right here, where this is a positive and that's a negative. And we're plotting the deflections in all the angles, all the distances. Okay. Notice the node is 0 because there's 0 deflections there. Got it? Yeah. Now, hopefully, this will help you understand the freshman question of how does the electron get from one side to the other going through the nucleus and not get stuck. Okay, this is not a particle spending some time on the top of the dumbbell and then spending some time on the bottom of the dumbbell. This is a spherical electron wave function that's oscillating in that direction. So the whole cloud is oscillating in the z direction. If I take you see it's going up and down in the z direction. If I take a snapshot, it's gone positive in the z direction away from the nucleus, and it's come too close in the negative z direction, and it's too close to the nucleus, and sometime later it'll go the other direction. So this is the oscillation of that electron wave function. It's a single electron smeared over the whole atom. It's not a particle hopping from one side of the dumbbell to the other. Okay, so that is an understanding of the wave function that is almost never taught. These are spherical harmonics, and the electron cloud is a sphere, and this is how it's vibrating. Okay, great. Now, one of the quantum mechanical postulates, the unprovable starting points that we started with at the beginning, and what Schrodinger put in his paper, was kinetic energy is where the electron is. Okay, so that's a postulate. That's a starting point. We haven't proven that. Okay, so if it's oscillating in the z direction and has 0 kinetic energy in the x and y direction, then this electron is spending it's sort of moving along the z-axis because of that postulate. Okay, so this cloud is moving along the z-axis. That's where it's going to do its directional bonding and so on, and we'll get to that bonding piece in the MO chapters. But then you have the deflections in the y direction. You have a 2py. Well, it's just deflecting in and out along the y-axis. And so that electron's position or probability of being found is along the y-axis, and the same with the x. So we have x, y, and z p orbitals. And we accurately say that their motion tells you where they are, and so they're along those axes, and they'll bond with things along those axes. So hopefully this long discussion about the deflection of a spherical shell helps you. Now, I think these are a little easier for me to do with my hands. Let's take this one right here. So I've got this motion, and it's bulging like that, and then it's bulging like that. So that's the oscillation for this 3D XY here. It's actually kind of tilted diagonally, so it's like this. So the z-axis is going up, and the x-axis is going this way, and so it's going diagonally between the z and the x axes, and it's going the other direction. And it's not moving here, and it's not moving there. It's moving in diagonally like that. And so that's, maybe I can see it and you can't, but I see that. I'm like, oh yeah, I see it. Okay, so this is a positive deflection, but sometime later it'll be negative. So you can put positives on these lobes and negatives on the other lobes. And whenever we see that plus minus pattern, we know that it's 2 axes times each other. So that's the xz, dxz. This is, again, that plus minus pattern in the xy plane, and so that's the dxy. If you need to review on that one, so you've got the z and x planes, And this is the pattern you would have if you multiply those by each other, right? So we have positive x and positive z times each other, we get positive numbers. Positive z times negative x, we give negative numbers. If they're both negative, you get positive again. And then if you have negative z times positive x, you get a negative number. So this plus minus pattern is what you get anytime you have two axes times each other. Now let's look at this really interesting one. Well, there's two interesting ones. These go along the axes, and so that would be the x squared minus y squared. So it's x squared, right? So the negative x's are positive 2 because they're squared. And then they're opposite sign of the y's. And so the y squareds mean they're both positive, but you change their sign by subtracting them. And so it's x squared minus y squared. It's the same kind of pattern, but it's on the axes, not between the axes. And then this, we always get lazy and call this the dz squared orbital. But it's actually the 2z squared minus x squared minus y squared orbital. Now, if I were to write out x squared plus y squared, that's the equation for a circle. So if I plot that, it's going to be the equation for a circle. Make sense? Okay. And in this case, I have the z squared. So these are going to be positive. And then I'm subtracting the xy circle. Minus x squared minus y. So that whole circle there is negative. So now you see this really weird shape, and algebraically it makes sense if you get it right. If you're not lazy and just call it a z squared orbital, it's z squared minus x squared minus y squared. And there's a 2 here, mainly because you're using the z direction twice, because you used it here 0. So this has 0z, and this has 2z, and we're using everything the same number of times, right? So we'll get to that in MO theory a little bit more too. Let's look at the F and the G orbitals. This goes up to I and J and K. They just keep going up and up and up. So you've seen the S, you've seen the P orbitals. Here's the D orbitals that we just looked at. Here's the F orbitals. And it gets more and more difficult. I can't do those with my hands. I can't really understand the math behind them as easily as I can the D orbitals. And so we'll go with their quantum numbers here. So this only occurs on n equals 4, 5, 6, and higher because L equals 3, and it's capped at n minus 1. So the first time we could have an F orbital would be n equals 4. And then here's your m sub L's. The first time we could have a G orbital would be n equals 5. And you say, but wait a minute, I don't see anywhere on the periodic table where we need G orbitals. Okay, never heard of a G orbital or an H orbital. We do the electron configurations for the ground state atoms, but we can see spectroscopy evidence that excited state atoms are using these orbitals. So the energy matches an electron hopping to, say, a 5G orbital or a 6H. And so they're there. They're just not there in the ground state for any of our atoms. So this magnitude of this angular momentum vector is quantized, and the z component of this vector is also quantized. And the energy doesn't depend upon the m sub L unless there's a magnetic field, or it could be an electric field too, but if it's the Zeeman effect or magnetic field, it's the Zeeman effect. If it's an electric field, it's the Stark effect. It's not Tony Stark, but it's something, you know. And then they have, because you have this angular momentum, you can think of it as a charge spinning in this orbital. That's going to create a magnetic field. And the electron spinning is a charged particle with intrinsic spin. That's going to create a magnetic field. And so we have this spin-orbit coupling where the electron spin couples with the m sub L quantum number. And we'll get into that with term symbols in atomic spectroscopy. So that's coming up as well. Let's look at the energy levels and then introduce this idea of a diagram called the Grotrian diagram. So over on the left is the energies we got from the Schrodinger equation. If we incorporate the angular momentum quantum number, so down here I capitalized it, but we can make it a lowercase l, 0, 1, 2, 3. So then this is an s orbital column, and this is a p orbital column, a d orbital column, and an f orbital column. And notice in a one electron system, the energy does not depend upon the angular momentum. So the 2s and the 2p have the same energy in a hydrogenic system. But when we get to multi-electron orbitals and energy levels, then the energy does depend upon the angular momentum in multi-electron atoms. And so notice how the 2p is a higher energy than the 2s, and the 3p is higher energy than the 3s, the 3d is higher than the 3p, and then we have this funny business where the 4s is actually lower in energy than the 3d. And so this gets back to what you remember from freshman chemistry, hopefully, the electron configurations. And so sure enough, we have electron configurations, and you've got to remember the ordering of these things. And there's that nice little tool that we have on the next page. But yeah, practice these. You've got to know the electron configurations well. And the twist that we're going to add onto this is we're going to do the electron configurations for excited states. Okay, we didn't do that in the freshman version of this. And we're going to do electron configurations for all those exceptions. So remember this little tool on the left? So it's really handy and still works, you know. So after that 3p, you fill the 4s, and then you come back up here and start filling the 3d. And then you go to the 4p, and then before going to the 4d, you go to the 5s, and then you come up to the 4d. So this still works, and we can fill out most of the periodic table with that tool. But the one case that we have trouble with are these exceptions, where if you're within one electron of a half-filled shell, a half-filled subshell, then sometimes you have these exceptions. So chromium, you know, if you were to follow this tool right here, it would give you this electron configuration. But experimentally, when we go look at it, it's actually this one. And so it's experiment that tells us the half-filled subshells are stable. Okay, that's an explanation of what we see in experiment. Okay. And so let's just finish up with this idea of multiplicity. So whenever we have an atom, we have this unpaired electron, we're looking at this, the orbital that it's in. So L equals 0 for that electron. We have one electron, so it's S equals 1/2, and multiplicity is 2S plus 1. Okay, so 2 times 1/2 is 1 plus 1, so multiplicity is 2. In all of these cases, I've put this in the notes. Are these written for you? Oh no, well we'll have to do these. Well, I'd say go to the video and look at these. But notice how all of these are multiplicity equal 2, because they all have a single unpaired electron. Even this 2p5, it's one electron away from 2p6 and being filled. So it has one electron left. And so, and that L is it's in a p orbital, so L is 1. It's one electron unpaired, so it's S 1/2 and a multiplicity of 2. So I just wanted you to practice on this. And so I put all of these examples in here that have the same multiplicity, the same spin, but a different L. And we ignore all of those shells that are filled. And so that's really the main point that I wanted to point out with this slide. So it's all in the video, so you don't have to try to cramp your hand trying to get this down. But what if they have multiple shells that are unfilled? We're going to do that next time. Okay.